Hello friends, I welcome you in lecture number 25 on relations. In this lecture we are going to discuss that how we can determine the properties of a relation using the graph of a relation. So that we are going to discuss in this lecture. Before that we just recall the properties of relations. We know that a relation R on a set is reflexive if it contains diagonal elements of this type. For every A in the given set, if order pair A comma A belongs to R, then relation R is called reflexive relation. In other words, every element is related to itself by the relation R. Second property we can discuss is symmetric relation. So for symmetric relation, condition is that if order pair AB is present in R, then if we reverse the order of elements, then order pair BA must also be present in relation R. In other words, if A is related to B, then we must have B related to A, and this is for elements AB in a given set. Another property we have seen is irreflexive relation. Irreflexive relation means this type of elements are not present in our relation for every A in a given set. That is, no element is related to itself by the relation R. We have also discussed antisymmetric property. Antisymmetric property says that if A is related to B and B is related to A, then A and B must be equal. In other words, if A and B are different elements, then either AB belongs to R or BA belongs to R. If A and B are different, then either A is related to B or B is related to A. This is antisymmetric property. And we have seen transitive property also. Transitive property says that suppose element A is related to B and element B is related to C, then we must have element A related to C. Now we can determine the properties of a relation using the elements or ordered pairs in a given relation R. But suppose we are not given the relation R and we are given the graph of the relation, or suppose we are given the diagram of a relation R, and using that relation we want to decide the properties of relation, then that also can be done using the graph of relation. Also we can decide the properties of a given relation. If we don't have to write down the relation from the graph, that also we can do, but from the graph itself we can decide that whether our relation is reflexive, symmetric, or some other properties. So suppose we are given the graph of a relation, and suppose we want to check whether relation is reflexive or not. Then for reflexive relation we require that every element is related to itself. So if every element is related to itself, then there must be a loop at each vertex A in the graph of that relation. If there is a loop at each vertex of the relation, then we can say that relation is reflexive. Now suppose we want to check whether relation satisfies this property, symmetric property. Then symmetric property says that if A is related to B, that is, if there is an edge from A to B, then B is related to A. That is, there must be an reverse edge from B to A. If there is an edge from A to B, then that means A is related to B. And symmetric property requires that if A is related to B, then B must be related to A. So there must be an reverse arc from B to A. So if there is an arc between two elements, or two vertices in the graph, then there must be a reverse arc between those two vertices for relation to be symmetric. So we can check whether there is an edge between two vertices. If there is an edge, then there must be reverse edge between those two vertices. For example, suppose I consider these three vertices, and suppose I have these three elements in the given set, and suppose I have A related to B and A is related to C and B is not related to C. So if this relation is symmetric, then here we can see A is related to B, so I must have reverse edge between B and A. Similarly, A is related to C, so therefore I must have reverse arc from C to A also. So this is the graph of a symmetric relation, because there is a reverse edge for every edge, or if there is an edge between two vertices, then there must be a reverse edge between those two vertices if our relation is symmetric. For irreflexive condition is that no element is related to itself. That means there must not be a loop at every vertex. If there is a loop at least one vertex, then also relation is not irreflexive. For reflexive, there must be a loop at every vertex, and for irreflexive, there must not be a loop at any vertex. Now for antisymmetry, we require that if two elements are different, then either A related to B or B related to A. That means if there is an edge from A to B, then there must not be a reverse edge. For example, if I consider again some graph, say suppose I am having these 3 or 4 vertices, then if A is related to B, or here we can see A and B are different, so either A related to B or B related to A is possible for antisymmetric. If we have antisymmetry, then either A is related to B or B is related to C. Similarly, I can draw an arc from D to B, but there must not be a reverse edge. Similarly, suppose we can consider this also. C and D are different, so there is no arc from D to C because there is an arc from C to D. So this is a graph of antisymmetric relation. For transitive relation, it is not so simple. For some graphs, we can check by observation that whether there is a transitive property satisfied or not. So we can decide the properties of relation using graph of a relation. If a relation is reflexive, then there must be a loop at each node, or at each vertex there must be a loop. If the relation is reflexive, then there is no loop at any vertex or at any node. If a relation is symmetric and if one node is connected to another, then there must be a return arc or reverse arc from the second node to the first. And for antisymmetric relations, no such direct return path should exist. For symmetry, if one node is connected to another node, then there must be a return arc from second node to the first node. So this is required for symmetry, and for antisymmetry, no such direct return path should exist. So here I have sketched several diagrams or graphs of the relations, and here we can check whether they are satisfying certain properties or not. We can see that this relation is symmetric. There is an arc as well as return arc for every vertex. You can see if I consider this as node representing x, y, z and say W. So we can see X is related to Z, then Z is also related to X. Y is related to Z, Z is related to Y. So this is an example of symmetric relation. The relation representing this graph is symmetric because whenever there is an arc between two vertices, then there is a written arc also. Here we can see there is no written arc, so we can say that this relation is antisymmetric. Here this vertex is connected to this vertex and there is no written arc. Similarly, for each possible pair of vertices there are no written arcs, so this is an example of antisymmetric relation. And here there is a loop at this vertex only. There are no loops at X, Y and W, so this is not reflexive. This relation is not reflexive because X is not related to itself. Similarly, Y and W are also not related to themselves. This is also not reflexive, but this is not irreflexive also because Z is related to itself. Here there is a loop at Z, that means Z is related to Z. So this relation is not irreflexive. This is irreflexive because there is no loop at any node. I have sketched these two graphs to explain transitive property. For transitive property, we have to check that whenever A is related to B and B is related to C, then A is related to C. So if there is an arc from A to B and arc from B to C, then there must be an arc from A to C. So that I have to check for transitive relations. So now here we can check, or we can see that A is related to B and I have to see whether B is related to some vertex or not. So B is related to D, that is there is an arc from A to B and B to D, so we must have A related to D, that is there must be an arc from A to D, so that is satisfied here. Now here A is related to C, but C is not related to any vertex. Similarly, we can check for B. B is related to D and we can check that B is related to D and D is related to C. So we must have B related to C. So here we can see B is related to C. And similarly, D is related to C, but C is not related to any other vertex. Similarly, D is related to C only. So this relation is transitive. We have checked all possibilities. Whenever A related to B and B related to D, we have A related to D and we have this also satisfied, and there is no other possibility to check for transitivity. So this is transitive relation. Here I have only two vertices X and Y, so we can see there is an arrow from X to Y, that is X is related to Y and Y is also related to X. Therefore we must have X related to X for transitive property, and we can see there is a loop at X, therefore X is related to X. Similarly, we can check that Y is related to X and X is related to itself, therefore Y must be related to X, so that is also satisfied. We can check in this way also, Y is related to X and X is related to Y, therefore we must have Y related to Y, so there is a loop at Y also. So this is also an example of transitive relation. So in this way we can decide some properties of relations using the graph of a relation also. Another way is, if you are not comfortable to decide the properties of relations from its graph, then you can write down the relation from its graph, and then you can check whether your relation satisfies certain properties or not. In lecture number 24 we have discussed how to write down the relation R from its graph. So if you are not comfortable directly from the graph, then you can write down the relation corresponding to given graph, and then you can decide the properties of that relation. So this is all about this session. I hope you like it. Thanks for watching.